Welcome back to the deep dive. Today we are taking a fascinating and deeply technical plunge into that one question that has just preoccupied everyone for centuries: life beyond Earth.
hmm
Our source material today is a really rigorous study of astronomical data and theory, and it's largely driven by the insights of Joseph Shklovsky, which, it really forced the scientific world to rethink everything they thought they knew about habitable zones.
That's right. Our mission here is to really extract the key insights from, decades of astronomical exploration. We're talking everything from the Soviet Venera probes to the American Mariner and Voyager missions.
So we're kind of abandoning the old ideas.
We're totally abandoning the notion that life has to look like us or, live where we live.
Yeah.
We're trying to identify where conditions might paradoxically favor these really strange forms of life, and maybe even more importantly, how life's fundamental building blocks could travel across the immense gulf of space.
It's a shortcut to understanding cosmic biology, and it starts with a truly shocking reversal. We're kicking off by analyzing what I think is the greatest planetary bait-and-switch in cosmic history.
Right, Venus.
For centuries, our closest, warmest neighbor, Venus, was heralded as this potential paradise. We really need to understand why that assumption was just so spectacularly wrong.
And how the subsequent research turned that, tropical fantasy into a suffocating, crushing nightmare. We'll start right there by overturning that historical optimism.
It's a real cautionary tale, isn't it?
It absolutely is. It's a tale about assuming similarity based on, well, very superficial attributes. And we're going to see why, ironically, the cold, dry environment of Mars is now considered infinitely more favorable for life than the intense hellscape we eventually found on Venus.
Okay, so let's unpack the myth of Venusian life. Why was this planet, which on the surface seems so similar to Earth, considered such an ideal place for so long?
Well, it was a perfect storm of positive observations, really. If you were just looking through an early telescope, Venus has almost Earth-like dimensions. Its size, its mass, its gravity, they're all pretty comparable.
Okay, so it looks like a sister planet.
It does, and it has a significant strong atmosphere, which was first noted by Mikhail Lomonosov centuries ago. And of course, that thick, persistent cloud layer.
Which hides everything.
Exactly. Plus, because it's so close to the sun, it gets nearly twice the solar energy that Earth does. So, all the inputs suggested a warmer, perhaps even tropical, sister planet.
So the visual and physical evidence was pointing very strongly to a world just teeming with potential. But as we developed better tools, the picture became, well, increasingly harsh.
Precisely, and the deception started right at the most fundamental planetary characteristic: its rotation speed. It's just a fantastic example of astronomers trying to solve a puzzle with, very limited tools.
Right, and the source material details this early detective work. Before we had radar, how did they even try to measure Venus's day length?
They had two main methods, and what's fascinating is that both of them led them completely astray. The first was spectroscopy, where they measured the Doppler shift of reflected sunlight.
So the light bouncing off the planet?
The idea is if the planet is spinning quickly, the light reflecting off the side coming towards you should be blue shifted, and the side moving away should be red shifted.
Makes sense.
And this initial analysis suggested a really rapid rotation period of about 4 days.
Okay, a 4-day spin, that's fast, but, manageable. What was the second method they used?
The second method involved tracking features on the cloud layer itself. Missions like Mariner 10 used UV photography, because UV light can sometimes see things that visible light can't, to observe these persistent features in the Venusian atmosphere.
And what did that show?
Well, again, tracking these features confirmed the 4-day period, so for a while it seemed settled, a short Venusian day.
Wait a minute, let's unpack this. Why were both of these observations, which agreed with each other, so completely and utterly wrong?
This is what's so fascinating. They weren't measuring the planet's spin at all. They were measuring wind speed.
The wind.
Yes. They were observing the high-altitude atmosphere, specifically the layer about 70 kilometers up, which moves roughly parallel to the equator. It's a phenomenon we now call superrotation. The entire atmosphere moves much, much faster than the planet itself.
So they were just tracking a weather pattern, essentially.
They were tracking extremely high-speed, persistent wind currents, not the rotation of the solid planet underneath all those clouds.
So we needed a tool that could physically see through that shroud. And that's where the radar revolution came in, using radio astronomy.
Yes, exactly. Radar was absolutely required to find the true speed of the solid body. We had to send a powerful narrowband radio impulse through the atmosphere and then measure the frequency broadening of the signal that bounced back.
A subtle effect, I imagine.
Very subtle, but it allows you to calculate exactly how fast the planet's surface is rotating.
And the findings, I mean, they weren't just surprising, they were cosmogonically bizarre. They revealed three really radical details about Venus's spin. Detail number one, the rotation is extremely slow, 243 days.
Which is just astonishing because Venus takes only 225 Earth days to orbit the sun. A Venusian day is literally longer than a Venusian year.
Wow.
I mean, just try to imagine that. Imagine having seasons that change faster than the cycle of dawn and dusk. That alone just throws out any idea of terrestrial-style environmental stability.
And detail number two, the spin is retrograde.
It rotates backward, clockwise, relative to its orbital motion. It's the opposite direction of Earth and almost every other planet in our solar system. This is a profound mystery that, it points to a very violent past, which we'll get into later.
And the third bizarre detail.
Its axis of rotation is nearly perpendicular to its orbital plane. So unlike Earth, which has a 23.5-degree tilt that gives us seasons, Venus is essentially bolt upright.
So no seasons at all then.
Combined with the slow spin, it means there's almost no axial variation or seasonal change. The thermal distribution is just incredibly complex.
So if you were standing on that surface, let's ignore the heat for just a second, the sun would only rise and set twice per Venusian year.
Roughly every 117 Earth days, yeah. And while the source notes this doesn't, completely exclude life, it certainly makes the environment profoundly challenging for any complex organism that relies on familiar day-night cycles.
It creates this incredible potential for heat extremes.
Exactly. Although, as we learned, the atmosphere is actually very effective at distributing that heat. And radar gave us one more curious coincidence. During its inferior conjunction, that's the point where Venus is closest to Earth, it always faces Earth with the same side.
That's a strange detail.
It's a highly stable orientation that suggests a powerful ancient gravitational lock between our two planets.
That's a fascinating, almost subtle piece of evidence for some deep cosmogonical link. But let's move from the slow spin to the real nightmare, the heat and the pressure. Before we sent direct probes, radio astronomy was already giving us clues about what was under those chilly cloud tops.
The initial data was ominous. The cloud tops are relatively cold, around minus 40 degrees Celsius. But scientists knew the clouds are transparent to longer radio waves, specifically those greater than 1.3 centimeters.
So they could see the surface with radio wave.
Exactly. And by measuring the thermal radio emission coming from the surface, they calculated an equivalent radio temperature that was incredibly high, 550 to 600 Kelvin.
Which translates to?
That translates to 277 to 327 degrees Celsius.
That's already high enough to sterilize almost anything we can think of. But you mentioned the readings varied based on the specific wavelength being measured.
They did. When observing shorter millimeter waves, the temperature readings dropped to about 400 Kelvin. And this difference is critical for understanding the atmosphere.
Why is that?
Because it's explained by atmospheric absorption. Specifically, the heavy concentration of carbon dioxide in the atmosphere was absorbing radiation at those specific short wavelengths. But the critical uniform reading across all the longer wavelengths proved the surface was uniformly hot, regardless of whether it was day or night.
And then, we finally got definitive confirmation from the Soviet space program. The Venera 7 and 8 probes were, absolute engineering triumphs to achieve soft landings under those conditions. What did they tell us directly?
They confirmed the horror show. Direct measurements near the surface clocked the temperature at approximately 480 degrees Celsius.
480 C.
To put that into perspective for you, that is hot enough to melt lead, aluminum, and zinc. This isn't just hot, it's industrial processing hot.
And the pressure.
The pressure was nearly 100 atmospheres. On Earth, every 10 meters you descend into the ocean increases the pressure by roughly 1 atmosphere. So 100 atmospheres is the pressure you would experience if you were about a mile deep underwater.
So the Venera probes were essentially landing in a superheated, ultra-compressed industrial oven.
That's a very good way to put it.
Let's focus on the cause. What is the atmosphere composition that creates this extreme environment?
It's the very definition of a runaway climate. The atmosphere is 97% carbon dioxide.
97%.
Compare that to Earth, where CO2 makes up less than 0.05% of our atmosphere. On Venus, you have trace amounts of water vapor, maybe 0.05%, some carbon monoxide, and various acids like hydrogen chloride and nitrogen fluoride. Nitrogen and noble gases, which dominate our atmosphere, make up less than 5% on Venus.
So that staggering concentration of CO2 is the engine driving this catastrophic greenhouse effect.
Precisely. The CO2, along with those small amounts of infrared-absorbing water molecules, forms this incredibly dense thermal blanket. Heat gets trapped, and its removal is extremely difficult. Once the planet lost its initial surface water, the process just became irreversible.
But the source material introduces an alternative idea, or at least a contributing factor, what they call Venusian meteorology, which was observed by Mariner 10. This suggests the heat might be complicated by some atmospheric dynamics.
Yes, Mariner 10 observed a persistent dark spot, often called the Eye of Venus, which was located near the subsolar point. This dark spot suggested massive, intense atmospheric flows, creating a gigantic, persistent, high-pressure zone.
What's the hypothesis there?
The hypothesis is that the solar energy is distributed across the entire planet through this really vigorous circulation system.
So if this circulation is orders of magnitude more powerful than Earth's weather systems, it might be the primary mechanism for distributing and maintaining that extreme surface heat, not just the simple blanket effect alone.
That's the debate. The extreme meteorology, driven by all that solar energy hitting that thick CO2 layer, might contribute significantly to the surface heat. It might even be the dominant factor keeping the whole planet uniformly hot. Regardless of the exact balance, the atmosphere is a violent heat transporting system.
Which brings us to the final, definitive word on Venusian life.
The conditions are just. They're simply too extreme for the chemistry of terrestrial life. The heat alone precludes the existence of complex organic chemistry, specifically the protein compounds necessary for life as we know it.
And the water.
More critically, the lack of a hydrosphere liquid water from the earliest stages of the planet's formation would have made the initial emergence of primitive life extremely difficult, if not completely impossible. Venus is a geological and, well, a biological dead end.
That slow retrograde rotation of Venus isn't just a quirky fact then. It's a profound cosmic mystery. We should pivot now and use that strange spin as a clue to explore the deep history of our solar system, particularly how Venus and Mercury might be related.
This is where we get into what's called cosmoconical significance, how the planets actually formed and evolved. And Mercury's rotation, which we also determine by radar, is also slow. It's locked into this precise ratio, exactly 2/3 of its orbital period.
So the two innermost planets are both strangely slow.
Exactly. The slow rotation of both of them suggests a common and perhaps very violent history that we really need to account for.
Standard solar tidal forces can't really explain something as extreme as Venus's deceleration and retrograde spin, right?
No, they struggle to. And that leads us to this truly radical hypothesis, which is supported by Shklovsky's analysis, that Mercury was once a satellite of Venus.
Wow. Mercury was Venus's moon.
It's one of the most compelling pieces of cosmic speculation. We know from our own Earth-Moon system how powerful tidal forces are. I mean, Earth once rotated in just a few hours.
And the moon slowed us down.
Right. So the hypothesis posits that Venus and Mercury formed a close double-planet system, maybe much closer than the Earth and Moon are today.
And given Mercury's significant mass relative to Venus, the tidal breaking forces would have been just immense.
Oh, exponentially so. These massive tidal forces would have acted as a gravitational brake, slowing Venus's rotation dramatically. And at the same time, the forces would have increased Mercury's orbital radius, pushing it further away.
Until it broke free.
The calculations suggest the system reached a breaking point where the gravitational bond was severed when Mercury reached an orbital distance of about 500,000 kilometers from Venus.
So the system underwent a massive gravitational divorce, basically. The resulting trajectory sent Mercury into its current solar orbit. If this happened, what evidence remains today? What are the scars of that breakup?
The residual evidence is so compelling because it solves several independent mysteries at once. First, it perfectly explains why neither Venus nor Mercury currently has any natural satellite.
You shed them violently.
Second, it accounts for Mercury's uniquely high orbital eccentricity. Its orbit is really stretched out, which is a common result of such a massive gravitational perturbation.
And it links back to that earlier radar finding.
Yes, the third piece of evidence. It explains that common orientation they maintained during inferior conjunction. Their shared history left them tidally linked, even when they separated.
And what about Venus's surface?
Finally, and most dramatically, the colossal tidal forces exerted by Mercury on Venus in those early eons could be responsible for the complex, rugged surface relief that radar mapping reveals on Venus today. The surface structure isn't just volcanic, It may be the permanent deformation left by its former massive moon.
That is a staggering thought. The very topography of Venus might be the residual energy of a gravitational battle from billions of years ago. Let's look quickly at Mercury itself then, as observed by Mariner 10.
Mariner 10 gave us our first clear look, and the surface looked strikingly familiar. It's just heavily cratered, very much resembling our moon.
And what does that tell us about its history?
It tells us two major things. First, there has been no dense atmosphere capable of causing significant erosion. And second, no powerful tectonic processes have been active over the last 4.5 billion years to smooth out that ancient relief. It's basically a geologically dead world.
And while Venus is uniformly hot because of the greenhouse effect, Mercury's extreme temperature swings are for a completely different reason.
It's brutal. It's because of the lack of atmosphere to distribute heat. The day side reaches plus 275 degrees Celsius, while the night side, facing deep space, plummets to minus 175 degrees Celsius. It's a world just defined by massive thermal stress.
To link this back to the broader implications of planetary formation, the source mentions that the farthest planet, Pluto, is also a highly unusual binary system with a large satellite orbiting very closely.
Right, the Pluto-Charon system. It features a satellite Charon that's only 5 times smaller than the planet with a very short 7-hour period. And this raises a fundamental question about how small planets form. Is this doubleness, this initial formation of close binary systems, a common characteristic for small planets in our system?
And if so,
If so, then the chaotic, violent nature of solar system evolution is even more widespread than we once imagined.
we've established that the inner rocky worlds are fundamentally hostile, either from runaway heat or massive thermal swings. So now, we leave those terrestrial disappointments behind and look outward to the gas giants. The source material argues that Jupiter and Saturn, and especially their satellites, are now considered significantly more promising for the emergence of life.
This is a classic example of a scientific paradigm shift. We're moving from the belief that life requires, external moderate warmth from the sun to the realization that life could be sustained by internal energy sources in environments we previously just dismissed as too cold or too deep.
Let's focus on Jupiter first. Shklovsky refers to it as a self-luminous protostar. That sounds like a bit of an exaggeration, but the data actually backs it up.
It's not an exaggeration at all. Jupiter's composition is 82% hydrogen and 17% helium, so compositionally it's very similar to the sun. But the key is its energy output. Jupiter emits 2.5 times the energy it receives from the sun.
So it's generating its own heat.
It is fundamentally generating and radiating its own heat. It's a massive self-luminous body in its own right, just not quite hot enough to start fusion.
Well, if it's not nuclear fusion, what is generating this colossal internal energy?
The source of the heat is gravitational potential energy. It's continuous, slow compression. Jupiter is just slowly collapsing under its own immense weight.
And that's enough to generate that much heat.
The calculations estimate that the planet only needs to contract by about 1 millimeter per year to fully account for all the excess energy it radiates. It's behaving like a tiny, extremely slow-cooling stellar object, just radiating away its primordial heat.
This changes everything for the potential of life, because its atmosphere is composed of hydrogen and helium, which resembles the primordial atmosphere of early Earth.
Exactly. Simple organic compounds could spontaneously synthesize in that atmosphere, stimulated by UV light, or, critically, by powerful electrical discharges. And we know those discharges exist because radio astronomy detected these incredibly powerful multi-second radio bursts from Jupiter, which scientists attribute to lightning storms on a massive planetary scale.
So you have the building blocks and you have the energy, but how do you solve the temperature problem? The top of Jupiter's atmosphere is freezing cold.
This is where the internal dynamics become the mechanism for life. Jupiter is subject to incredibly turbulent convective movements. Think of them like massive, rapid turnovers of the atmosphere. These movements are powerful enough to carry those newly synthesized organic molecules down through the freezing upper layers to depths where the pressure and temperature are suitable for complex organic synthesis.
And what's the temperature range we're talking about for this theoretical habitable layer?
We're talking about a layer where the temperature is roughly between 0 degrees Celsius and 50 degrees Celsius. That's the sweet spot for liquid water to exist, if it were there, and for complex organic chemistry to proceed. The turbulence acts as a biological elevator, creating this constantly mixing vast potential habitat deep within the clouds.
The Pioneer and Voyager missions provided the critical data that proved this environment is as energetic as we theorize. Let's talk about the challenges Pioneer 10 and 11 faced just to get there.
I mean, they faced fundamental engineering problems. Because the solar flux at Jupiter is 27 times less than what we get at Earth, solar panels were completely useless.
So how did they power them?
Mission planners had to rely entirely on radioisotope thermal generators, or RTGs. They're essentially nuclear batteries that use the heat from decaying radioactive material to produce a continuous 140 watts of power. They were running on internal heat, just like Jupiter itself.
And if the distance wasn't enough of a challenge, Jupiter has the most terrifying radiation environment in the solar system.
Oh, the magnetosphere is immense. Jupiter's radiation belts are just unimaginably powerful. The intensity starts doubling every 10 hours as you get closer, and at 700,000 kilometers out, the level was pushing the absolute limits of the onboard equipment. The spacecraft needed heavy shielding just to function.
And Pioneer 10 also confirmed two separate magnetic fields, right?
Yes, two distinct fields. There is a non-symmetrical Earth-like dipole field generated by the internal dynamo, but there's also a secondary massive magnetic field directly associated with and generated by those immense radiation belts and all the charged particles trapped within them.
Yet, despite those extreme conditions, Pioneer 10 gave us those phenomenal, exceptional color images of the cloud layer and the Great Red Spot.
Those images confirmed the vigorous energy transport we were talking about. We saw the rapid changes, the massive storms, the deep structure of the clouds. It all confirmed that the atmosphere is in constant, violent motion, reinforcing that idea of deep convective transport.
But the truly game-changing revelations came to the Voyager missions, particularly when it came to the satellites. First, the ring.
Yes. Voyager confirmed the existence of a faint, thin ring around Jupiter, which was a huge sensation at the time. But what's fascinating is that its existence had actually been predicted years earlier by the Soviet astronomer S.K. Vyseksviatsky.
How did he do that?
He analyzed old photographs of this persistent equatorial strip and correctly theorized there must be a ring, though his idea was largely dismissed until Voyager actually saw it.
And then Io,
Yeah.
the innermost of the big Galilean moons.
Io is critical because it has a thin atmosphere, and it's a massive source of influence on Jupiter's electromagnetic environment. It acts almost like a cosmic lightning rod, influencing Jupiter's long-wave radio bursts. But the absolute biggest surprise, the discovery that fundamentally changed the search for life, was the detection of active volcanoes by Voyagers 1 and 2.
That must have been a jaw-dropping moment for the mission scientists, finding active volcanoes erupting on a moon that far from the sun.
What is the source of that heat?
It's not radioactive decay or primordial heat, it's tidal flexing. Io is constantly being squeezed and stretched by the immense gravitational pull of Jupiter and its neighboring moons, Europa and Ganymede. This constant internal friction generates tremendous heat.
So it's gravitationally heated. And that proved that life could potentially be sustained by a non-solar gravitational energy source, which was a radical idea in astrobiology at the time.
Moving briefly to Saturn, does it share Jupiter's internal energy characteristics?
It does. Saturn is also self-luminous. It radiates about twice the energy it receives from the sun, and it's powered by that same continuous compression mechanism. Pioneer 11 did key research there, including on Titan, and confirmed that the famous rings are indeed composed of small ice fragments, maybe about a centimeter in size.
So if we look at these internally heated worlds, we have to assume that life, if it exists, would have a completely alien biochemistry, perhaps centered around a different solvent than water, given the low temperatures and composition.
Exactly. Since those organic compounds we discussed might be dissolved in, say, ammonia or water droplets in the cold lower cloud layers of these gas giants, the source forces us to confront a fascinating hypothetical, the possibility of ammonia-based biochemistry.
Right. We are so entrenched in this planetary chauvinism, assuming carbon and water are required. But scientifically, water is just a solvent. Could ammonia really replace it?
Theoretically, yes. Liquid ammonia has properties that are highly analogous to water, which makes it a viable theoretical medium for life. It has a relatively high specific heat, so it holds energy well. It has excellent solvent properties, capable of dissolving many organic and inorganic compounds.
And the temperature range?
Crucially, it exists as a liquid over a reasonable temperature range from minus 70 Celsius to minus 33 Celsius at 1 atmosphere of pressure, a temperature range that you can actually find in the upper atmospheres of gas giants.
But how do you reconstruct the complex chemistry needed for heredity and metabolism, things like amino acids, proteins, and DNA, by just swapping out the solvent?
You establish a complete chemical analogy based on substitution. On Earth, our biochemistry is based around oxygen ions, O-, and hydroxide ions, OH-. To create the ammonia analog, you just replace the oxygen ions with the amine group, NH-, and the hydroxide ions with the amine, NH2-.
So you're creating a parallel chemical universe.
That's a perfect way to describe it. This substitution allows for the theoretical construction of ammonia analogs for everything. Amino acids, complex protein compounds, even nucleic acids like DNA and RNA. The theoretical framework for a complete parallel heredity code is totally viable.
And the metabolism would be completely reversed from ours. What would their waste products be?
Well, if we follow the analogy, the process that corresponds to oxidation, which is critical for energy generation in us, would be the attachment of NH- or N- ions. The final metabolic waste products would not be water and carbon dioxide, but rather ammonia and cyanogen.
So if we could somehow observe these hypothetical ammonia organisms, they would effectively drink ammonia as their primary solvent and potentially breathe nitrogen compounds, excreting cyanogen. That is a truly alien vision of life.
It forces us to confront the immense potential for variation in the cosmos. However, the author concludes this section with a very important caveat. While the possibility is fascinating and scientifically consistent, the probability of such primitive, purely ammonia-based organisms on gas giants is considered very low, and this skepticism is reinforced by the spectroscopic detection of water vapor in Jupiter's atmosphere, suggesting that water may still be the preferred solvent even in those cold, deep environments.
We've established that life's emergence is difficult, requiring either external solar energy or massive internal heating. So now we shift our focus entirely. What if life didn't emerge here at all, but was delivered from space?
This takes us to the robust evidence for organic material originating in the cosmos.
Well, right, and this brings us to the carbonaceous chondrites. These are rare, only about 1% of stone meteorites, but they are highly significant because they're rich in carbon, up to 3%, as well as sulfur and water. They are untouched, pristine samples of the early solar system's chemistry.
And what complex organic findings have scientists actually extracted from these rocks? Oh, a massive array of complex compounds. It proves that the basic chemistry of life occurs spontaneously throughout the galaxy. We find high molecular weight, paraffin hydrocarbons, various fatty acids, and remarkably, compounds resembling cytosine, which is a crucial component of DNA and RNA. The building blocks are literally everywhere.
And the definitive proof that these organics were created in space and not from contamination here on Earth came from the Murchison meteorite, which fell in Australia in 1969. This is the cornerstone of cosmic chemistry, isn't it?
It is the single most important piece of evidence. Chemical analysis of Murchison found 16 types of amino acids. Now, 5 of these were among the 20 amino acids used in terrestrial life, which means space is already making the exact components we use. But 11 types were completely non-terrestrial and never before seen in Earth biology.
And the crucial detail that ruled out contamination was the asymmetry, or the chirality. Can you explain why that LR mix is such powerful evidence?
Of course. Amino acids, the building blocks of protein, exist in 2 mirror image forms, left-handed, or L, and right-handed, or R, all known life forms on Earth. Every single bacteria, plant, and animal use exclusively L asymmetry amino acids.
Only the left-handed ones.
Only them. The Murchison meteorite, however, contained an almost perfectly equal mix, 50% L and 50% R forms.
So why does that balance prove they're from space?
Because biological processes on Earth inherently favor L forms. A 50-50 mix is the expected outcome of random, abiotic, non-biological synthesis, like you'd get in chemical reactions within a dust cloud or on an asteroid. That LR ratio is definitive proof. These were born in space.
So the building blocks are everywhere. The next massive leap is whether actual life travels. And this is where we run into these reports of fossilized microorganisms in meteorites.
There have been these isolated, very intriguing reports. Oval inclusions that morphologically resemble algal spores. These inclusions even stained with biological reagents and luminesced under UV light. But while it's compelling, the source material urges extreme caution here.
Why is that?
Morphological similarity alone is insufficient, and scientists are incredibly wary of contamination, especially during retrieval and lab analysis.
But these ideas inspired cosmic transport hypotheses, like the one from Bernal.
Right. Bernal had a more imaginative version of transport. He suggested that during a massive volcanic eruption on an inhabited planet, spores or microorganisms could be ejected with dust into space, possibly even achieving escape velocity.
And then what?
They might then stick to a passing meteorite and be carried across vast distances, eventually returning home. It's a mechanism for closed-loop transport, though achieving that initial escape velocity is a massive, massive hurdle.
That sets the stage for the full panspermia debate, the idea that life originated elsewhere and was seeded here, which was famously proposed by Svante Arrhenius back in 1907.
Arrhenius argued that tiny spores could survive the vacuum in the cold and then be propelled across interstellar space by the pressure of stellar light. It was a really attractive idea because it sidestepped the thorny question of how life spontaneously arose here on Earth.
And Carl Sagan, he attempted to put some numbers to this interstellar journey. What were his optimistic estimates?
Sagan calculated that very small spores, maybe zero point 0.2 to zero point 0.6 micrometers in size, about the size of some viruses, could be ejected from an atmosphere by electrical forces and then propelled by stellar light pressure. He estimated they could reach Mars in weeks, the outer solar system in years, and the nearest stars in tens of thousands of years.
Which sounds like a long time, but on a cosmic scale, it's nothing.
Biologically, it's a blink.
But the author, Shklovsky, critically refutes these optimistic travel times and, more importantly, the survivability. This is where the physics of the journey become absolutely lethal. What is the first objection regarding the travel time?
The first objection is the actual mechanics of motion in interstellar space. Sagan assumed a straight line rectilinear motion. But in reality, interstellar space is filled with these vast, turbulent gas clouds. Spores don't move under constant light pressure. They move mostly like dust particles, carried along by these clouds, experiencing what's called Brownian motion.
So a random zigzag path.
Highly irregular, random movement, yes.
And what does that irregular movement do to the total time required for the journey?
It catastrophically increases the transit time. The calculations show that for a spore to cross the entire galaxy using this mechanism, it wouldn't take millions of years, as previously hypothesized. It would take hundreds of billions of years.
Hundreds of billions.
That's 10 times the current estimated age of our entire stellar system. Panspermia would literally take longer than the universe has existed in its current form.
And billions of years of cosmic travel exposes the spore to a threat that Arrhenius couldn't have possibly quantified. Massive cumulative radiation damage.
This is the second, and I would argue the most devastating objection: radiation death. Over hundreds of millions of years, a spore traveling through the galaxy would be bombarded by approximately 10 billion cosmic ray particles. This results in an absorbed radiation dose of several billion roentgens.
Wait, stop right there. How lethal is that dosage compared to the resistance of life on Earth?
It's thousands of times higher than the survivability threshold. While some terrestrial spores, like Nanopoccus radiodurans, are incredibly resistant and can withstand up to 1 million roentgens, several billion roentgens is a fatal sterilizing dose. There is no known biological structure, no matter how protected, that could survive that amount of cumulative radiation exposure.
The physics basically dictates a cosmic sterilization event.
It does. And even within our own solar system, the immediate threat from our own star is enough to kill a traveling spore.
That's the third objection, right? UV sterilization.
Yes. The sun's ultraviolet radiation, especially those short wavelengths below zero point 0.3 micrometers, is highly lethal to microorganisms. Calculations show that even if a spore was launched from an asteroid, it would receive a deadly UV dose long before it even reached Mars's orbit, unless it was shielded deep inside a dust particle or a rock crevice.
Which is a very specific and unlikely condition for the simple panspermia model.
Exactly. So, simple, random panspermia driven by light pressure is effectively ruled out by the physics of time and radiation. And this left scientists needing a different model for cosmic seeding, which led to the highly controversial idea of directed panspermia proposed by Francis Crick and Leslie Orgel.
So, not random, but intentional.
Directed panspermia suggests that life was intentionally seeded on Earth by an advanced extraterrestrial civilization, maybe using a specialized shielded probe containing microorganisms. They weren't arguing for the mechanism, though. They were arguing based on two suspicious biological features of life here on Earth.
Okay, argument one. The universal genetic code. Why is that a sign of external seeding?
Well, the observation is that every known life form on Earth, from the simplest archaea to the most complex mammals, uses the exact same fundamental genetic code. Now, if life had arisen independently and randomly on Earth, you might expect to find multiple, regionally distinct genetic codes, or at least minor variations.
And we don't.
We don't. Panspermia offers a simple explanation. The code is universal because it came from a single, external, universal source.
And argument two is even stranger. the reliance on rare elements.
Yes, the chemical anomalies. They noted that crucial biochemical processes on Earth rely disproportionately on elements that are surprisingly rare in the Earth's crust, particularly molybdenum.
Mm.
Meanwhile, chemically similar and far more abundant elements like chromium or nickel play very minor roles in our biochemistry.
So why the fixation on a rare element?
That's the question Crick and Orgel asked. Could this reflect the unique composition of a specific, perhaps molybdenum-rich planet where life originated?
These arguments are highly speculative, of course, but they illustrate how even the fundamental accepted truths of terrestrial biology can be leveraged to suggest origins far beyond our own planet.
The final, and I think most philosophical step in this dive is to challenge what the author calls planetary chauvinism, this belief that life must arise and evolve only on planets. We need to expand our search for habitats far beyond the traditional zones.
And this was clearly a serious topic of discussion in the scientific community. The source mentions a 1971 symposium that even considered the possibility of life in the atmospheres of very cold stars.
That's how far they were willing to push the paradigm. And while life on cold stars was ultimately rejected due to massive energetic difficulties, it's just too hard to sustain the necessary chemical gradients. It paved the way for more serious, non-planetary proposals.
The most famous of these came from the physicist Freeman Dyson, the comet hypothesis. His argument was purely statistical, based on surface area.
He argued that the sheer number of comets in the galaxy exceeds the number of stars and planets by many orders of magnitude. And while they are individually small, their total surface area available for chemical reactions is just astronomical. Furthermore, we know the central regions of comets are rich in complex organic molecules. Statistically, they offer the largest volume of potential habitat in the galaxy.
But the reality of a comet as a biological incubator is, well, pretty grim.
Oh, they are highly unsuitable. They lack gravity, which is often considered a prerequisite for complex structure. Their orbits are highly eccentric, which leads to extreme temperature fluctuations, from deep space frigidity to total vaporization near the sun.
And they just fall apart.
They're highly volatile environments, constantly disintegrating into meteor streams. They have the building blocks, but they absolutely do not have the stability.
Finally, the source pushes the boundaries of conception entirely, looking at life that might not even be based on chemical elements or traditional planetary environments. We're talking about life in the most abstract sense possible.
This is where theoretical physics meets extreme biology. First, there's the hypothesis of subnuclear level life, which was proposed by Cocconi. He pointed out that given the existence of over 200 known elementary particles, far exceeding the number of stable chemical elements, a complex replicating system could theoretically exist at the subnuclear level, a kind of nuclear chemistry.
A system built not from atoms and molecules, but from the complex interactions of fundamental particles. That is, that's utterly outside the framework of biochemistry as we understand it.
It suggests that life is simply a pattern of complex replication, and that pattern might manifest at scales and densities we haven't even begun to process. And even more abstract is the concept of Friedmans, proposed by the theoretical physicist M.A. Markov.
Friedmans, that's a term that sounds straight out of science fiction. What are they?
They are hypothetical, almost closed worlds in a cosmological sense. They are objects that, from the perspective of an external observer, might appear as very small, perhaps elementary, charged particles. They represent a level of organized complexity that exists entirely within its own gravitational and quantum constraints.
And the fascinating thing here is that, while it's highly speculative, the source notes that Markov's idea of Friedmans does not violate the fundamental laws of physics. It shows that the limits of our biological imagination are still far narrower than the limits of physical possibility.
It's the ultimate challenge to our assumptions, isn't it? We assume life needs stable gravity, moderate temperature, and chemical gradients. But physics allows for replicating systems at scales we can barely process, forcing us to ask, is life defined by carbon and water, or is it defined by the mathematical pattern of replication and complexity itself?
This deep dive has truly spanned the immense listness. From the industrial heat and pressure of Venus, a world of beautiful destruction, to the subtle, self-generated warmth of a protostar like Jupiter. We've seen how the violent gravitational dynamics of the early solar system might have ejected entire planets, leaving lasting stars.
And the critical takeaways, I think, are clear. While Venus confirms the extreme rarity required for life to emerge and survive in the inner solar system, the robust evidence from meteorites proves that the organic building blocks of life are absolutely ubiquitous in space. The building materials are everywhere.
But the great challenge remains the journey. The physics objections, the colossal time required for random travel due to Brownian motion, and that fatal cumulative dose of billions of roentgens from cosmic radiation, they seem to definitively rule out the simplest version of panspermia.
Which leaves us with a truly provocative closing thought, and it draws on the most radical ideas we discussed today. If organic building blocks are confirmed to be everywhere in comets, meteorites, and interstellar clouds, and if we accept that planetary systems are formed through violently complex mechanisms, such as the hypothesized ejection of Mercury from Venus,
Then what?
then should we focus less on where life starts and more on the extreme accidental mechanisms that might transport it, protected deep within massive, shock-ejected planetary debris across seemingly impassable distances? The origin may be simple, but the secret to life's presence on Earth may lie in the incredible, violent journey it took to get here.